Okay, I think most people are here already, so let's just get started. Um, this is going to be the last lecture, except for the lecture on meta-analysis of next week. So I got a question from someone whether there will be a question on the exam, and well, the answer is yes, to reward people for actually going to the lecture, but of course it will be a very superficial question because it's only one day away from the exam. So if you went to the lecture, you will know the answer. If you didn't go, then well, watch the lecture and then you'll know. Okay. On Monday we have the graded assignment. I just want to, tell you guys one more time what to expect. I will explain it in the morning. It takes about 15 minutes to explain. I've scheduled for it, and then you have a good 3.5 hours to work on it. Of course, you can take a break in between. I really don't think anyone needs 3.5 hours. It should be doable. Okay, if you're proficient in R, you should be able to do it in like 20 minutes. But I don't expect you to be proficient in R. So let's say an hour or an hour and a half. Then really most people should be done with the main part, and you should be looking at the bonus questions or make a nice plot or change your code to get a higher grade. Because the graded assignment, you have to pass the exam and the graded assignment. There's a minimum grade for both of a 5, I think. I will confirm with Harold. And there's a minimum average grade of 5.5. But there's really no reason to fail the graded assignment if you've been to the practicals. So it's a way for you to, slightly boost the score you get on the exam, because it counts for 15%, I believe. But let me, don't quote me on that. I will ask Harold. Okay. This morning we had the practical on PCA. If you have any further questions on that, we can do that during the Q&A, or you can post them on Brightspace. But there's two things I want to do right now. I want to do a Q&A about the practice exam, but also just about the stuff that we have covered so far. And I want to show you how all the methods relate that we have covered in the second and third week. The first week was mixture of advanced and basic, so don't put too much weight to whatever has been said in the first week. It's really the second and third week that matters for basic statistics. Okay, let's start with this. This is Mentimeter. So this allows you, also the people watching online, you can go to menti.com and enter this code. So this is a way that both the people online and the people here can participate. I think it also works on your phone. Then you enter this 8-digit code, and you can enter up to 8 subjects that you found difficult, or terms, or skills, just so we have an idea of what I should be focusing my attention on during this 2-hour maximum Q&A. Let's take a couple minutes for this, 5 minutes, so you can all fill some stuff in, and then I know what I shouldn't be wasting time on and what I should pay more attention to. Okay, we're getting somewhere. Okay, 16 respondents. Let's give it another minute and then we'll start talking. Okay, now it jumps up. Okay, I'll start talking as it updates. I see a lot of people say model selection is difficult. I'm kind of happy to see that because that is the most difficult part. I'm happy that it doesn't say t-test or something or linear regression. Model selection is difficult, and I'm not going to give you 10 different measures and tell you, okay, you make a choice which model is better. If there's a question on the exam about model selection, you will be given one measure on which to decide, or there will be one test shown, and it will be between only two models. So don't worry about it in the context of the exam. In the context of your internship, it is difficult. So feel free to contact us through the ibl.statlab@gmail.com email address. We provide consultancy mainly to third-year bachelor students, but you guys haven't had that opportunity, the basic statistics students, so we also offer it to you. After that you can still contact us, of course, and we will try to help you, but there's a limit to the amount of time we can spend on it. So don't worry too much about model selection. Ancova, we will recapitulate that. GLM, I kind of expected that. It is the more difficult of the subjects. PCA, we just covered it, but we can go over it again. Then I see some smaller things. Quasi-Poisson, just forget about it. Let's see. Negative binomial. I don't know. Did Howell talk about negative binomial in his lecture? Okay, then you don't have to know the negative binomial distribution for the exam. Everything, okay. We only have 2 hours though. Programming in R, okay. If you're for the graded assignment, if you are working alone, try getting in contact with a group that doesn't have 4 people yet. There's a limit to 4 people, but with 4 people and the exercise that you've done the other days and the solutions to the exercise of the other days, don't worry about the graded assignment. Nobody who has come to the practicals fails it usually, so I'm willing to make an exception for you. No. The point is, a lot of people after GRS, so the third year bachelor course, will say, well, I don't think anyone is really proficient in R after this course. And it's like, did you think I learned this in 4 weeks? If you are able to use a script that someone else wrote and adjust it so it works for your code, that is a useful skill, because you can also do that during your internship. And for the purpose of this course, that is enough. So I really wouldn't worry too much about programming. Now, multiple testing, if there's anything in particular, I will recapitulate it briefly, but if there's anything in particular, just ask a question during the lecture and we'll go over it. Okay, then, let's see. We have the practice exam. We can either start with a recap of the subjects in order, or just go over the practice exam. So, any preference?
We can go over the practice exams.
Yeah, it's a good idea. They are more or less in order of the subjects that we treated. So let's do that. I will go over the practice exam, and then in the meantime explain the subjects that are explained there. That are asked about. Okay, so just to make it absolutely clear, this is an old exam. This is the first year I am teaching this course, so I didn't make this exam. Different teacher, different things that they find important. So this is not 100% representative of what your exam will be, but I will point out the important differences. The most important differences is when I say I don't care about something, then that means it's not going to be on the exam. So there's a question down here somewhere about the Shapiro Wilk test. I've all told you my love for the Shapiro Wilk test, so there's not going to be a question like this in the exam, because personally I think that testing for model assumptions is a silly approach to modeling, so you don't have to memorize this at all. Okay, so let's get started. The first question, I will answer it, but again, this is not a question that I am planning on asking, because we didn't really talk about this. So Yeah, there are several steps for a correct statistical workflow. Anyone have an idea? Doesn't have to be 5, but how would you start your analysis?
Pulling data. Look at the data flow.
Yeah, quality of the data.
Yeah, so plotting data, quality of the data. Basically, yeah, of course, in practice, it depends on the size of your data. If you have like 100 dimensional data, yeah, a summary isn't going to be very helpful. But for the problems that we have been doing for the past couple days, the first thing I would do is just check that your data are read correctly into R. So you can do this with str or with summary or something like that. Just make sure that a factor is a factor, a numeric variable is a numeric variable, etc. And then the second thing would be to plot your data. You will very often see people with questions not understanding output of their model, and they didn't even plot their data at all. And then, yeah, you're just missing out on things that could be obvious, like outliers or interactions or curvature. So you should always plot your data during the course and after it. And after that, what do? We've checked the quality of our data. We've tried to make a plot. Yeah, we fit some sort of model. So we make a choice for, depending on the research question, a test or a model, and we apply it. And after that, yes, very important, diagnostic. So every test and model comes with a set of assumptions, and only under those assumptions is inference valid. So we do diagnostics to check if there's any serious violations from those assumptions. After that, yeah, provided everything is okay in the diagnostics, we produce a summary and then we get to the conclusion. Okay, if the diagnostics don't look okay, what could we do?
Transform the data.
Yeah, transformation. Anything else?
Correction.
What kind of correction?
When we do multiple testing.
Um, That comes all the way at the end. So all the way at the end, you determine which of these tests are important for my conclusion, and then you correct them for multiple testing. Yeah? Yeah, choose a different model. And that can be as simple as leave a certain variable out, or add an interaction, or remove an interaction. That's a different model, and it will produce different residuals, so your diagnostic plots will also look different. Yeah, and sometimes it's as simple as, well, you didn't specify the model right, you need an interaction, and then suddenly the diagnostics look fine. Yeah? Okay, second one. Yeah, this one, again, is not something I stressed during the course, so it's not going to be on the exam, but let me just answer it anyway. If you're doing Ancova, okay, let's start by what is Ancova? Yeah?
It's when you have continuous and categorical variables, explanatory variables.
Yeah, so it's a type of regression analysis where you have both continuous and categorical explanatory variables. That's all there is to the meaning. There are ways to interpret it, but you don't have to know that. Okay, what do you think are the assumptions of Ancova?
Independence.
Yeah, that's the most important one, independence. So you assume that each observation is independent of each other.
Normality of the error.
Yeah, normality of the error term.
Equal variance.
Yeah, but equal variance, when I hear that, sounds like you're talking about group. So to be specific, when we're talking about regression analysis, I would say constant variance. Yeah, there is a term for it, but yeah, I like to keep the language as simple as possible. But if you search for this online, it is also called homoscedasticity. Okay, any other assumptions? Yeah, linearity. This is a linear model. So yeah, we do assume that the relationship can be expressed in terms of intercepts and slopes. And if that doesn't capture the relationship, then linearity is violated. Okay, number 5, that's why this won't be a question on the exam. Will probably be something like there are no outliers, but I don't think this is an assumption. Outliers can be real data. So the thing is more that you should check for outliers, you should check for leverage to make sure that your results aren't the result of only one or a few observations, because if they are, you need to be very confident that that is real data and not some misplaced decimal separator, or that, oh, something went wrong during experimentation. Okay, then the next two questions I think are more of the kind that you could expect on my exam as well, because I think it's really important if you're going to do any kind of test that you know what is a p-value, what is a confidence interval, what is a null hypothesis, what is the false positive, and what is the false negative. So here's the question, what is a type 1 error and how can the probability of a type 1 error be reduced? Okay, let's start with what is a type 1 error? Yeah, false positive. And what does that mean? When you shouldn't, yeah. Yeah, so a false positive is when you reject a null hypothesis even though it is true. So it is when you have a significant p-value even though the population doesn't really have a difference. Okay, yeah, how can you reduce the probability of a type 1 error? There are many ways, by the way, so how could you do that? I couldn't quite hear that.
Maybe increase sample size.
Yeah, if you only increase the sample size, you will increase the power, right? So the chance that you reject the null hypothesis actually becomes bigger. That doesn't affect the chance of a type 1 error though. Yeah, multiple testing correction. If there's more than one comparison involved, you should apply a form of correction because the total chance of a type 1 error becomes way bigger. If you only do one test, how can you reduce the chance of a false positive? I see you're raising your hands with your eyes. No? Yeah?
Like shedding another alpha?
Yes, exactly. We determine the chance of a type 1 error. It is alpha. So if you set alpha lower, you are more strict about what counts as significant, and the chance that you will incorrectly tell that something is significant is lower. Yeah, so it's as simply as choosing a different value. Okay, then, what is the generic equation of the t-value? So by that I mean not specific, but just in general, what is the t-value? Yeah? Yeah. Every t-value is a difference in means divided by a standard error. Now, that standard error can be anywhere from very simple to quite complex, but in general, it's just a difference in means divided by some form of uncertainty, which we call the standard error. Now, in linear regression, you can get a t-value by doing estimate divided by standard error, right? So why is that still a difference in means? Because it's still a t-test. Okay, so in linear regression, when you have the output of a linear model, you see a bunch of p-values, right? And you see the t-values from which those p-values were calculated, and that t-value is equal to the estimate divided by the standard error. But why is that a difference in means? Because we just agreed all t-tests are difference in means. Yeah?
Because the estimate is actually like the intercept. It's a difference between the intercept and the value that the other variable will take. So it is a mean. No.
You're close, but not quite. Yeah?
I wanted to say the same thing.
Okay.
But maybe rephrasing is we are actually subtracting 0, which is the point, like the intercept.
Yes, exactly.
In which the null hypothesis. No. In yes.
Yeah, so, okay, I told you many times the p-value for the intercept itself is usually not interesting. Why? Because all of those p-values are a comparison of the estimate to 0, right? It's a one sample t-test, and the value under the null hypothesis is just 0. So it is a difference in means, it's just the difference with 0, which is the same as just estimate divided by standard error. Yeah? What does the t-value measure? What does it tell us? Again, don't think too difficult, don't think specific. We have a generic equation of t-value, which is some difference in means divided by some standard error. What does this t-value tell us?
A higher p-value means that
Close, yeah.
Not the probability that you'll get a value that high in like in the graph.
That would be a p-value.
On the t, you also have the t graph, don't you? Yeah.
Yeah, we'll show that one later. But it's that's the x-axis for that figure. That's the t-value. Yeah. No? Sorry? I think you're all thinking too difficult. The t-value is your evidence against the null hypothesis, right? For a t-test. And the bigger it is, the less likely the null hypothesis. Or at least the less likely that your data were produced under the null hypothesis, if we're being strict about correct language. Okay, next one. This one I think we have practiced several times, so this shouldn't be an issue. We already talked about this. The t-value is the estimate divided by the standard error. You can compute all of the missing values that way. You will never be asked to calculate a p-value, because how would you calculate a p-value? Yeah? If it were like 100 years ago, I would have said yes. Yes, of course, that can be done, but it can also be done more precise. This has to do with what is the p-value.
The probability that this sample, if the null hypothesis were true.
Yeah, close. So not this sample, but a sample with this larger difference or larger. Yeah, but okay, so the way to calculate the p-value is to calculate the surface area under the t-distribution. And that is an integral, right? In high school math, if you want to know surface area under a function, you have to calculate the integral. Okay, let's have a look at the t-distribution. And then we will know both why people used to use tables, and we will know why we never ask for a p-value on the exam. This is the probability density function of the t-value. This is a gamma function if you've never seen it before. It is a limit. Yeah, this is the integral of the t-distribution. This takes a long time to evaluate, especially if all you have is a basic calculator. So we do numeric integration, which is what we do with R. So that's why we never do it in this course, trying to calculate the integral, because it's pointlessly difficult, and we live in an age where computers can do it very precisely, very quickly. Okay, there were some people who said they found Ancova difficult. So let's go over the output of this model. In the next, we have to draw the graph in the plot below. So that's actually pretty much interpreting the output. So let's see, can I maybe do this? Okay, one moment. I'll make this as big as I can to preserve resolution. And then we're going to draw. Okay, let's draw. Where do we start? Oh, sorry, let me quickly check for questions because I don't have Wi-Fi. Call a statistician. Yes, exactly. Okay. Yeah, we're going to draw. We have the output over here. If it's too small, I can zoom in and out. And you're going to tell me where am I going to start? How am I going to draw this? Yeah, we're going to start with the intercept. That's where you should always start. For any linear model, will save you a headache. So, where is the intercept? Where do I have to draw it? Yeah, on the y-axis. Be careful. Not over here. Why not? Yeah, because that's not 0. 0 is over here. Yeah, so be careful. The intercept is 20.8, so that means that where x, in this case fructose, is 0, that's where I'm going to draw this 20.8. Okay, 20.8 is around here. Yeah? Agree? Okay. What do I do next? Slope. Yeah. Okay, let's do that. We have fructose. So indeed, that's what we have a slope for. So how are we going to draw this intercept? Sorry, this slope. Let me quickly go up. But then how steep should my line be? Should it go up or down? And how much? Okay, when should I be down by 0.4? Where on the x-axis should I be at 0.4? Here? Okay, so it was more or less correct, but let me explain why. The slope is the difference in the outcome when the explanatory variable goes up by 1. So we look at the x-axis over here, 1. This one is where it should be down by minus 0.44 something. Okay, if you have trouble drawing this precisely, of course you can be a little off, that's not a problem. How could I make this more precise? Because I could start here and then draw like this. But that's, if you do it pen on paper, it's probably going to be off a little. How could you do it more precise? You don't have to for the exam, just asking.
You take each value of x's at 1, 2, and 3, and then measure your
Yeah.
and then just draw one.
Yeah. Okay, so you could draw a point, first here, then here, then here. That works. But the thing about a line is it only goes in one direction. Yeah, so we really only need the value at x is 3. Right, so just calculate the x the furthest away that you can still draw, which should be like 1.5 down. So we should be around here, right? Something like this? Okay, and then from here, wait, let me do that differently. Like this, and then I can drag it like this. Okay, what relationship does this show? Because we have one line, but we have 3 different treatments. What have we just drawn? Let me drag this up a little so I can make it bigger. And then let me get rid of this. Okay, so which line have we drawn? Yeah?
Between fructose and treatment 1.
Yeah, exactly. This is only the slope for treatment 1. Why is that the case? Sorry?
That's the reference group.
Yeah, it's the reference group, and we have estimated an interaction in this model, right? And that means that the slopes are not equal. Okay, what's the next thing we do? Okay, let me quickly interject. Did anyone calculate the missing values? We can do it here, but if we already have them, it's quicker. Okay, we'll do it here. Okay, which one shall we do first? This is the easiest, right? Because this is just the t value. Hey, what is this? Yeah, so I'll just copy this, and I will use R. You can use a basic calculator on the exam. Okay, so the first missing value is this. I'm just going to add it in the plot. Yeah, you can use a basic calculator. I think there will be a laptop, because the exam will be on ANTS. I don't know if you've ever used it. It's an online system to make an exam. So we are arranging that there will be laptops for everyone, and on the laptop there's a built-in calculator. Yeah?
Internet on the platform as well?
Yes, but very restricted. It really only allows you to get to the exam. But nice try. Okay, I gave you the first one. How do we calculate this one? Yeah, so that's this one divided by this one. It's just flipping it around. So let's do that. Let me copy this. Yeah, so second value is about minus 15. Yeah? Oh yeah, you're right. Wait, is this correct? This, yeah, that makes, does it? We can check. We can just divide this one by the answer, 1.5. It's about 3. Wait, we have a t-value is equal to estimate divided by standard error, right? This time we have no estimate, so we want the estimate on the other side. Okay, first thing, we multiply the t-value by the standard error. Alright, then we're already there. Okay. So, let me copy the right values. This one times this one is minus this. Okay, last one. How do we do this one? How do we calculate the standard error? Yeah. Yes. Okay, so it's this one divided by this one. And then we can continue, right? Because now it's a little easier to answer the question because we have all the values in the table. Okay, what are we going to draw next? We have here, let me write it here to be absolutely clear. We have the effect of fructose for treatment 1. So fructose treat 1. Yeah? Or I can just say treat 1 because fructose is already on the x-axis. Okay, what's the next thing we're going to draw? Where are we going to start? Yeah?
The intercept for treatment 2.
Yeah, the intercept for treatment 2. Where are we going to draw it?
On the y-axis.
Yeah, so?
Where zeros.
Yes, where it's 0. And then?
It's 3.1.
Higher than what? Yeah, so we go to where x is 0 again. And then we look at the estimate. And we add that to the intercept. Yeah, so now we are at 20.8 plus 3.2. Then we draw it at 24. Unless I'm too tired and also miscalculating that. Okay, now we have a new intercept. What do we do next? Okay, a slope. How are we going to draw the next slope for treatment 2? Yeah?
Isn't the fructose plus, minus 1/4?
Yeah, exactly. So be careful with this. The interaction is the difference in slopes. So we have to do this one plus this one. And that's about minus 2, right? So this one goes down by minus 2 every time that x goes up by 1. Well, and that looks like this. Yeah?
Do we add them up or do we
Yes.
subtract them?
No, you add them up, but they are both negative, so it will become more negative. Yeah?
Yeah.
Okay, so yeah, not very nicely done, but doesn't matter. Treat 2. Yeah, is that clear to everyone why I drew it like this?
Yeah.
Okay, good. Yeah, okay. So, if there is an interaction in your model, that means not all slopes are equal. If there weren't an interaction, this would be very simple, right? We would just draw a line parallel to the one we already drew, like so, more or less. Yeah? But they aren't parallel because we estimated an interaction. Now, what does the interaction tell us? It is the difference in slope. Yeah, difference from the reference group. Now, the reference group has its own slope. It's minus 0.4497. And the difference in slope is minus 1.47. We add those two coefficients, which is about minus 2. And then we can draw our second line. Yeah, because we already determined where it starts. Yeah? Okay, what do we do next? Hmm? Yeah, what do we do?
We have the intercept of the movement 3 fructose to the intercept point, so it's 20.6.
Yeah, so we add the estimate. Sorry, what'd you say?
But we're going to start from the 0 at 20.6.
Yeah, careful. This is the interaction.
Yes.
Oh, yeah, minus 2 and minus 0.
Yeah, so if we're looking for the starting point,
Oh.
we're looking at this one, right?
Okay.
This is the difference in intercepts. So then we start at 18.6. Okay, let me draw that. 18.6 is somewhere over here, right? Okay, and then what is the slope of this one? What makes you think so? Okay, I wouldn't count that wrong because indeed there's no significant difference in slopes. But this model does say that the average difference is this. Yeah, just the fact that it isn't significant, that doesn't matter until you draw confidence intervals or prediction intervals. If you're just drawing lines, you're drawing the point estimate, and the point estimate is minus 0.27, so it's 0.27 lower than the slope that we had. So where do we end up? At around? Yeah, so about 0.7 in the negative. Yeah, so it's fructose slope plus the treatment 3 fructose slope adjustment. Yeah, so that's about minus 0.7. So let me try to draw that correctly. It is about this, I think. Yeah, and indeed it isn't significantly different. You can also see that they don't differ by much. Yeah, the treatment 1 and treatment 3. So let me draw that. Treat 3. So this is an Ancova with interaction, which I think is the hardest that you can probably expect. If you were able to follow this, and if you're able to interpret the rest of the output, then, well, you may still find Ancova difficult, but for the exam, you'll be fine. Okay, how much variance does this model explain? Yeah, 82.6%. And if I were to ask you on the exam, okay, but what is the adjusted R squared for then? Similar, but a little bit different. Not multiple testing. Yeah, exactly. It is the variance explained adjusted for model complexity. So what is this measure used for? Yeah? Yeah, for comparing different models. Okay, let me explain to you why we use this adjusted R squared. If you have two models, one with an interaction, one without an interaction, the thing is, a model with more degrees of freedom will always explain more variance. So this r squared always goes up if you add more variables. But that doesn't mean it's a better model, right? Because you're also making it more complex. So that's why we can adjust the r squared for the model complexity, and then we can compare one-to-one which model explains more variance given its complexity. So it's a measure used for model selection. Okay, what do we see in the last line? Is it big enough, by the way? Okay. Yeah?
There are 54 degrees free.
Yeah. Okay, so what was the sample size of this experiment? Yeah. There's two places you can see it. It says the residual standard error has 45 degrees of freedom, and there are 6 effects, so it's a sample size 60. And also the F statistic says that after the intercept there are 5 effects which are assessed for significance, and it has 45 degrees of freedom left, 54 degrees of freedom left. So this one also adds up to 60. Now, what does this test tell us? This F test. Can anyone remember? Yeah?
There is somewhere a significant value within a model.
Yeah. So we are estimating 5 different effects. This is an omnibus test. This is the variance explained by the model divided by the residual variance. That's this 51.34. And yeah, that comes with a p-value. Okay, we haven't used it in the course, but what could you use this for? Where did we also see this test? Yeah, Ancova. And what did we call it? This test has a name. Yes, omnibus.
Okay.
And the purpose of the omnibus is to see if there's any difference. So it's a protection against false positives, because if you have a long list of significant p-values, maybe that's just a fluke. Maybe it's a coincidence. So yeah, you don't have to use it for all I care, because I told you all to correct anything for multiple testing. So, but if you didn't do that and you didn't know any better, then it's it's a useful measure to see. Okay, wait, is there anything explaining any variance explained by my model? Yeah.
You just come up with testing units because 6 effects we need to calculate an over to 7.
Okay. When you correct for multiple testing, you only use the p-values that you use for your conclusion, the ones that are directly relevant to your research question. The reason being that maybe we didn't even want these p-values, right? If all I'm interested in is there an interaction, I have to correct for how many tests? There are a lot of answers. How many coefficients pertain to the interaction? 2. The 2 tests have been performed to determine if there is a significant difference in slopes. So I would only have to correct these 2 if the question was, is there an interaction? If I want to use all of these estimates, then it's 6. But remember, the intercept is almost never an interesting thing to test. Okay, it doesn't start at 0. What gives? If that's not part of your research question, then you should only pick these 5 to correct. Yeah, and also with Ancova, this test is already a protection against false positives. It's like, if you were to use this in Ancova style, then step 1 is look at this one, and only if this one is significant do you look at these. So this one is also not part of the correction, this p-value for the F test. So if this were my research and I wanted to know all of these coefficients except the intercept, I would correct for 5 tests, because that's the number of p-values that you actually use to write up your conclusion. Like, this was significant, this wasn't. Yeah, definitely. If this one isn't significant, then we shouldn't even continue. Yeah?
But then you say, why don't you just
Because Okay, so if this one is significant, there is significance difference somewhere. The question is where. It's not another test for another difference. Yes, but the second one, okay, the second one you can only look at if the first one is significant. So that's not the same as doing two independent tests. Okay, let's see, can I ask something else about this? Oh yeah, what if I wanted to compare treatment 2 to treatment 3? How could that be done? Yeah, releveling. And what does that mean? Yeah, changing the reference group so that the difference group is in the intercept. Okay, let me quickly check if there were any questions in between. Not yet, okay. Okay, shall we continue with other questions? Yeah, how much variance to explain, we already answered. Must the null hypothesis regarding the slope of treatment 1 be rejected? And what is the correct way to state this? Okay, yeah, that second part is the important part. So, treatment... Alright, the slope of treatment 1, which one is that? Which p-value is the slope of treatment 1? Little louder, please. That's the intercept of treatment 1. What is the slope of treatment 1? Yeah, the one that says fructose. Okay, should we reject this null hypothesis? And how do you state the result in this case? What did you say?
Depends on the alpha.
Yeah, of course, it depends on alpha. So you should... Okay, if I ask a question like this, I will state alpha. But let's say alpha is 0.05. What do we conclude? Yeah?
That it's higher than alpha, so you can reject the null hypothesis.
Yeah, that is the correct way to state it. Be careful not to say there is no...
Significant.
Yeah, you can say there's no significant linear effect, but you can't say that there is no effect, because just because you didn't find it doesn't mean it isn't there. You know, it's like this is the thing with null hypothesis testing. If I want to know is there a snake in the grass, and I walk around for 1 minute and I don't see a snake, and the p-value is 0.8, say, well, it's non-significant, so I have evidence that there is no snake in the grass. Of course, I have some evidence that there may be no snake in the grass because I did walk around for 1 minute. But if this field is 1 square kilometer big, then that evidence is very weak. So you can't say that there is no effect. You can only say that you did conclude a significant effect or that you failed to conclude a significant effect. It's just one of the downsides of using hypothesis testing. Yeah? Okay. Yeah, so this is, what is this? What are we looking at? Yes, this is a model comparison. What would I conclude based on this?
That model 2 is significantly better than model 1.
For basic statistics, I would count that correct. But let's be a little precise with the language here. What is model 2 better at? What does better mean?
It's more proximity.
Yeah, that's the one. It explains significantly more variance. How can you see that? Yes, exactly. What does RSS mean? Anyone remember? Yes, residual sum of squares. So it's the squared difference from the actual value and what the model predicts for each value. Now, the lower that value, the lower the variance of the residuals, right? The less variance there's left in the residuals. Okay, which of these models is more complex?
Model 1.
Yeah, model 1 is more complex. So which of these models would we use if we want the one that explains the most variance? Careful. This one has a lower residual sum of squares. Yeah, this one is number 1. That's the more complex one. So this just tells you there is significant difference between these models. It doesn't tell you model 2 is better. It tells you there's a difference, and you have to look in the table which one is the better one. If they don't differ significantly, what would I choose? And why? Yeah, because it's simpler. But that's important. If they don't differ significantly, and your point is to get a model that explains as much variance as possible, then you would do the simplest model, because you're basically saying, well, I can make it more complex, but it doesn't add significantly more variance explained. That a question? Oh yeah. Okay. One way to see it is that one has an interaction, the other doesn't. Another way to see it is to look at the residual degrees of freedom. The model with the largest residual degrees of freedom is always the simplest. Yeah, because it has more degrees of freedom left. Yeah, that's about all we can say about this one. Okay, yeah, this is, I think, a more difficult one. What are sources of overdispersion? Let's start one simpler. What is overdispersion? Yeah, there specifically, so she said there's too much variance. That is correct. Specifically, there is more variance than the distribution that you assumed for your GLM encompasses. So, for example, if you take Poisson, then it has only one parameter that represents both its mean and its variance. So it's possible that it estimated the mean correctly, but that the variance is actually bigger than the mean. And the Poisson distribution cannot account for that. So if you would use the p-values of that model, it would be optimistically biased. So it would be biased towards significance. Yeah, I used the correct wording there, but you don't have to remember that exactly. The point being, there's more variance than there is in the distribution you chose. Okay, what are sources of overdispersion? Yeah? Sorry? Yeah, you excluded a variable that does have an important effect, so you didn't capture the systematic part of the process. What's another source of overdispersion? Sorry? Oh. There's at least one more potential source of overdispersion that you should always check for. Yeah, no interactions. So not necessarily another explanatory variable, but another explanatory effect, interaction. Yeah, that could be a reason. But there's still another one I'm looking for. Let me check if anyone online managed to answer it. Yeah, Gregorio. So large degrees of freedom means more estimates. Careful with that one, because we are looking at the residual degrees of freedom. So that means the degrees of freedom left. And if there's more degrees of freedom left, then we used fewer of them. Okay, source of overdispersion, I'll give the answer. Outliers. Because what is an outlier? It is an observation that's very far away from the rest. So it will by definition have a large residual. Square that large residual, it will inflate your variance. So when you detect that there's overdispersion, don't immediately jump to solutions specifically for overdispersion, but have a look at your data if all the values are realistic. Okay, a Box-Cox transformation of 2 for a linear model, blah blah blah, is proposed. How would you transform this model? What would you change to this model if Box-Cox suggests 2? There's a table.
Can we use that table?
No.
So we need to know what the...
I mean, you need to know, but you can reason them. Because what does Box-Cox suggest? Sorry? Yeah, but what part of my data? Yeah, the outcome. These are suggested transformations for the outcome. So in this case, and in many cases it's called y. So what does 2 mean? Yeah. You were almost there. Box-Cox suggests power transformations of the outcome. So if it says 2, that means your outcome to the power of 2 would give the best linear fit. So yeah, and 2 we call what? Something to the power of 2? Squared. Yeah, so yes, there is a table, but you know, the things you should really know is that y to the power of 2 is y squared, y to the power of a half is square root of y to the power of minus 1 is 1 divided by y, and that's it. Yeah? Okay. What is the concept of power, and which variables affect power positively? Anyone remember what power is?
How much variance it is,
No. Yeah, that is the only correct interpretation. It is your ability to reject the null hypothesis. So it is your ability to pick up a real effect or a real difference in the population. Yeah, and the power is a number between 0 and 1, so you can interpret it as a percentage, like I have an 80% chance that if there is a difference in the population, I will pick it up, or a 90% chance, or whatever your power is. Which things affect power positively, which things increase power? Sample size, yes, definitely. That is the most obvious thing you should increase first, if you can. What else affects power positively? Yeah?
Complexity of the model.
Yes, definitely. And in which direction does it affect your power?
The more complex your model is, it makes your power also higher.
It depends. If there is an interaction in your data, for example, and you don't include it, then the model without interaction will be weaker because it has larger residual variance, right? Because there's something in the data that you didn't fit, and that will increase the residual variance. But if two models are both more or less correct, then the simpler one will have more residual degrees of freedom, so it will have more power, because residual degrees of freedom is why increasing the sample size increases your power. Okay, but what else affects power? Yeah? Yes, definitely. If you have a bigger difference or a bigger effect or a bigger slope, that is more easy to pick up. So that means that your power is greater. Your ability to pick it up is bigger. There is one more. And let's let go of the positively part. There's one, okay, there are two more things that affect power.
Less residuals?
What about the residuals?
Should be less.
Well, you mean there should be fewer of them?
Yeah, I guess.
But the number of residuals is how much residual degrees of freedom I have. And if I have more power. So you don't want there to be fewer of the residuals, but you want the residuals to be smaller, yeah, because then your residual variance is smaller. So the variance negatively affects power. Larger the variance, smaller your power. Okay, finally, there's one more thing that affects power. It's a bit tricky, yeah?
There are outliers.
And in what way will that affect your power? Yeah, that will negatively affect your power. If there's an outlier, an outlier always has a large residual, which means the residual variance goes up, and that means that your power goes down. That's a good one. I didn't even think of it. But there is one more thing, I'll just tell it, it's a bit tricky. It's alpha. If we set alpha very strict, then we're very strict about what counts as significant. So your ability to detect a difference that significant is lower. Yeah, and if you set it less restrictive, like 0.1 or 0.2, it's easier to pick up a difference that is not that significant. Yeah? Yeah, lower variance, definitely. Yeah. Okay. What are the 3 elements of a GLM? Yeah?
The error structure, linear, and the link function.
Yeah, so a GLM consists of an error structure, a link function, and a linear part, or linear equation, or linear function.
Can I ask something?
Yeah, of course, yeah.
You said the bigger the alpha is, the more significant, the more power has the.
Yeah. Yeah, because lowering alpha reduces your chance of a false positive, but yeah, if you take alpha bigger, you have a big chance of a false positive, but the chance of a false negative goes down.
So
And
you
power
must
is
have a
1 minus.
balance.
Sorry?
You must have a balance, not
Yes, yeah. That's also why in the multiple testing assignments there was a question like, if you're worried about false positives, why not just lower alpha? And the answer is that that will cost you power, right? So you want to do it in the most efficient way possible. And yeah, one way to do that is FDR correction. Okay, so we have the 3 parts of a GLM. Does anyone know how they are related?
Yes. The link function.
Could you speak up a little bit?
Yeah, the link function relates the first one to the second one, so the error structure to the linear
Part,
equation.
yeah. Yeah, so the link function, it translates the linear equation, so eta, to the mean of the outcome. That's all you have to remember. If you just say the link function translates one to the other, that's also enough. If we want to be more precise, we have to talk about the canonical link function, but for this course you don't have to involve that in your answer. So if you just know that the link function is the thing that translates the linear part to the error structure, that is enough. Okay, comment on the diagnostic plot. I specifically said I wouldn't ask a question about this, so I will go over this real quickly. Yeah, this is a test for normality. What does it mean when this test is significant, you think? Yeah? That is really hard to show, because that's like saying, what is the chance that my data are 0? That's really hard to express. So there is no test that will tell you the chance that your data are normally distributed. There are only tests like this one that can tell you the chance that your data, that's the chance that your data would have arrived under a normal distribution. So if this one is significant, then your data are not normally distributed. Which means also that's kind of useless, because just because it's not significant doesn't mean that your data are normally distributed. Same for this one, NCV test. Yeah, NCV is non-constant variance. If this one goes off, it means there's significant non-constant variance. But if this one is not significant, then that doesn't really say anything about your model. So yeah, I'm not going to add these to the exam. Okay, then these plots. I will quickly show you how to interpret them, but it's not going to be an exam. Yeah, these are 3 different ways to look for outliers. The first one you already know, right? On the y-axis it says Cook's distance. So what would you be looking for? And yeah, but how would you conclude it's an outlier?
If it's above 1.
Yeah. So if it's about 0.5, you should take a look at it. If it's about if it's over 1.0, then it's statistically speaking an outlier. Okay, second one is the studentized residuals. Yeah, that just means minus the mean divided by standard deviation. Yeah, we didn't discuss this one. Oh, where did we go? Yeah, we didn't discuss this one, but you can just see this dotted line is around 0, so you can see which are more far away from the rest, right? So this is a large residual, this is a small residual. Then we have the Bonferroni p-value. This is a p-value for outlyingness. And it's corrected for the number of residuals you have, because of course this would constitute about, what is this, 50 or so tests, so this is corrected. Yeah, if this one is very small, like this, 0, then statistically speaking, this test thinks it's an outlier. But remember, the Cook's distance says, well, no, I don't think so, it's just 0.6. Then the hat values, we didn't talk about that, but yeah, we're just not going to talk about it because it wasn't part of the course. Okay, extra sheet, no. Yeah, so that's a practice exam. Are there any other questions about the practice exam or about the actual exam? How long is the exam? Let me check. Oh yeah, there we are. Okay, the exam is on Wednesday, 9:15 until 12 o'clock. If you have dyslexia, you need to show some sort of card. If you don't have that yet, that's okay, but I will write on the list that you still have to show me a card at some point in the future. And then you can get some extra time. Nobody should need extra time. I won't make it super long. But if you are worried about the time, there will be extra time for people with dyslexia. Any other questions about the practice exam? Yeah?
Can you use calculators? Because you said you can do it on that as well, but you don't find that very nice to work with.
Yeah, I mean, I don't find it nice to work with either, but unfortunately, you have to do it. Yeah. Yeah, so it's a laptop. I've asked for a space at the University Sports Center. I still haven't gotten the confirmation, but I will let you know as soon as I do. The University Sports Center, if you don't know, is on the way to the Gorlees building. That way, I think. And the way it works is everybody gets their own laptop. You don't have to bring a laptop. And it has a very restricted internet access. So you can access the exam, but you can't just start Googling stuff. Yeah, I mean, if the majority wants, it is an option to make it open book, but before everybody says, oh yeah, nice, and I don't have to remember many things, the level of difficulty of the questions will be a lot higher with open book, because I assume that you're able to find everything. Yeah, I hear a resounding no, so it won't be an open book exam. I have shown you which formulas you should know. Yeah, I think it's about 5 of them, and the other ones, you don't have to know the formulas, it's more about understanding the concepts. Okay, I also noted in the schedule that I had a brilliant idea to explain you about StatLab after the exam, but I think most of you will want to go home or sleep or party or something. So let me do it now. I already talked about this briefly, but we have this service for third-year bachelor students where during their bachelor internship they can send an email to ibl.statlab@gmail.com to ask for help with any part of their research project that concerns statistics. This includes study design, by the way. The thing is, we can only cover a limited number of topics in these 4 weeks, and maybe you're like, yeah, I'm pretty sure I have to use a GLM, but I don't feel quite confident using it yet. Send an email and we'll help. If you think like, yeah, my data are not independent, what can I do? We can suggest something, and if it doesn't take too long, we can write a model for you. The only thing is that, yeah, we get a lot of questions, so please take some time to formulate your question structured, not too long also, and if you have data, try and arrange it tidy, so one row is one observation. That also saves us a lot of time. Yeah, and if you're just completely clueless, we will still try to help you, but there's a limit to the amount of time we can invest in every question. Yeah, it's not actually for master students, but yeah, first of all, you guys haven't had the third-year course here, so until you get to advanced statistics, you can use it, and we can allow a little bit more time than the master students for it. But also after that, I mean, we are the statistical department here, so you can always ask for help, but we might ask that, we have some agreement of co-authorship or something if it takes a considerable time investment. Yeah? So that will save you another, I don't know why I wrote 2 hours for this. Yeah. Okay. Then
How long
That's-
does it usually take to grade the exam?
how long does it take to grade? Okay, good question. So no promises here, but the reason you guys have your exam before advanced statistics, okay, of course your course is worth 1 credit less than advanced statistics, so it should take less long. But also, yeah, for us it would be way easier to do them all on the same day. But then it would take a lot longer to grade your exam. So I'm going to try and grade it before the end of the week of the exam. Yeah, worst case scenario 1 week later. Yeah?
Graded assessment as to exam, or
Sorry?
both the graded assessment and the exam, or?
Yes, they will both be. I'm going to try my best to grade both of them within the week you had them. Where do you find the grades? Okay, of course I'll put them on Brightspace just by study number, so you can look up who you are. If you don't have access to that, you can just send me an email and I will send you your grade. Okay, let me make sure that we've had everything. Different tests have different power depending on when you apply them. Yeah. Sorry to reply to this very late, but that is correct. If you can assume equal variance, for example, then the equal variance test is more powerful. Yeah. Special what? You probably need your your ask something number and then your password. The things you use to sign into the network. If all else failed, we will make sure there is a printed version because we know this is the group of people not originally from Leiden University. So she asked, how do you need to sign into the computer on ANTS? I'm pretty sure it's with your university account, but we realize not everything is going smooth in the first few weeks. So I will print them, so there's also a backup option in case nothing works on the laptop. Yeah, and then you can just use the laptop as a calculator. Okay. Yeah, that was a bit shorter than I anticipated, but I think that's good. Yeah. Oh, yeah. The last thing I want to say in the schedule, there's some scheduled time for self-study. If you want, we can send 1 or 2, maybe 1, because I don't think a lot of people will come. But we can send an assistant here, because in this time I have to be at the advanced statistics course. But if you want, and you still want to ask questions, of course you can come to the Van Steenis building and just ask Harold or me. But if you're like, well, I just want to ask a whole list of questions, it's going to take a half an hour or something, we can ask an assistant to come over here. Yeah? Because in the schedule for advanced statistics, it says self-study selected topic. That doesn't apply to you. You don't have to do anything new after the, except for the meta-analysis lecture, but that one is special. Okay, I don't think there are further questions, so yeah, let's enjoy the weekend maybe. Okay, anyone online, you know the drill. You can ask questions on Brightspace. If you still don't have access, just send an email to the usual email address and I will reply. Have a nice weekend.